The SU StackUp program stacks without needing to pre-sort your traces. For example, you can make a CDP stack from shot-ordered traces. But SU StackUp will also stack to any key or any combination of keys. Therefore, you can make shot stacks and receiver stacks. This video is mostly about why you might want to make shot stacks and receiver stacks.
The SU StackUp program has 5 notable differences compared to SU Stack. 1. SU StackUp does not require pre-sorted traces. For instance, it can produce a CDP stack from shot-ordered traces or from any other trace order. 2. SU StackUp will stack to any combination of key names. For instance, it can stack on the FLDR key, a shot stack, and it can stack on the GRN, ORS, and GAPS keys, a 3D receiver stack. 3. SU StackUp allows specification of 2 range limits based on any keys. 4. SU StackUp stacks in double precision before outputting normal single precision traces, which is more accurate and more consistent than SU Stack. 5. SU StackUp makes each output trace header from the input trace that has the minimum offset distance for that output location. Example setups of SU StackUp for shot stack, receiver stack, and CDP stack, along with wiggle displays. Note that the same input file is used. No SU sort of the input traces is needed. Examples similar to this can be found in Demos Geom3D SU StackUp. Everybody should know what a CDP stack is and what it is good for. But what is a shot stack and what is it good for? And what is a receiver stack and what is it good for? Well, a CDP stack is subsurface consistent, but shot stacks and receiver stacks are surface consistent. So first I'm going to indicate what surface consistent means. Then I'll show some examples of how SU StackUp can be used with surface consistent problems. Notice the signal paths through the slow layer under shot A are roughly the same for all the signal coming from shot A. And the paths in the slow layer under shot B are also all roughly the same. This is because this near surface layer is much slower than deeper layers, which results in almost vertical travel paths near the shots. The result is that every trace from shot A takes the same amount of time to travel through the near surface layer directly under shot A. And every trace from shot B takes the same amount of time to travel through the near surface layer directly under shot B. Similarly, the signal paths through the slow layer under receiver C are roughly the same for all the signals arriving at receiver C. And the paths in slow layer under receiver D are also all roughly the same. Again, this is because the near surface layer is much slower than deeper layers, which results in almost vertical travel paths near the receivers. The result is that every trace going to receiver C takes the same amount of time to travel through the near surface layer directly under receiver C. And every trace going to receiver D takes the same amount of time to travel through the near surface layer directly under receiver D. You will have noticed that the slower layer has different thicknesses near shots A and B and receivers C and D. One of the purposes of surface consistent statics is to compensate for the differences in the slow layer near the surface. But surface consistent means the same compensation must be applied for all traces from each shot, and the same compensation must be applied for all traces going to each receiver. You do not have to apply all the surface consistent compensation at once. For instance, you can apply a time shift to all traces of shot A and then apply another time shift to all traces of shot A. Generally, the first time shift is called elevation statics or refraction statics and is a time shift to correct to a particular elevation, a datum elevation. That time shift is computed by replacing the slow layer velocity with another velocity, the replacement velocity. The difference from the true surface elevation to the datum elevation is also replaced by the replacement velocity. It is difficult to compute the velocity and thickness of the slow layer. This means that after elevation statics and/or refraction statics, there are still surface consistent time differences among shots and among receivers. These time differences are called surface consistent residual statics. These surface consistent time differences can often be displayed by using sustackup to make shot stacks and receiver stacks. A shot stack is exactly what it sounds like. After NMO correction, all traces from a shot are stacked together. A receiver stack is exactly what it sounds like. After NMO correction, all traces going to a receiver are stacked together. Next, I show traces for a nice simple fake 2D survey. Shots at the left end of a nice simple fake 2D survey. Shots at the right end of a nice simple fake 2D survey. Some of those shots with NMO correction applied. The NMO correction velocity is slightly wrong to make it a bit more realistic. Now I use sustackup to produce a shot stack, a receiver stack, and a CDP stack. The shot stack of that nice simple 2D survey. The receiver stack of that nice simple 2D survey. The CDP stack of that nice simple 2D survey. No surprises in those three stacks. Now, let's put some surface consistent statics on one shot and one receiver. Display of left shots with the same time shift added to all traces of one shot. Display of right shots with the same time shift added to all traces of one receiver. The shot stack again. One shot has a clear time shift relative to the others. The receiver stack again. One receiver has a clear time shift relative to the others. The CDP stack again. Very hard to see the effects of the time shifts in this stack. Let us put some dip on that nice simple 2D survey. Shot stack for dipping survey. One shot still has a reasonably clear time shift. Receiver stack for dipping survey. The one receiver with a time shift is not so clear. The CDP stack for dipping survey. Now, an offset range limit is specified in sustackup for the stacks, as shown above. Shot stack using a limited offset range. One shot has a clear time shift. Receiver stack using a limited offset range. One receiver has a clear time shift. CDP stack using a limited offset range. The CDP stack is becoming fuzzy near the location of the shot that has the time shift and near the receiver that has the time shift. So why is the receiver stack with limited offset better at showing the one receiver time shift? The answer is that a receiver stack is summing traces that cover a large subsurface area. When dip or other structure exists, the reflections do not occur at the same time in those traces, and therefore the receiver stack traces become unfocused. Limiting the offset range results in stacking the traces of the receivers over a smaller subsurface area, which reduces the unfocusing. Will limiting the offset range show a different time shift for the receivers or shot? No. Remember, surface consistent means the same time shift exists on all traces to a receiver and all traces from a shot. Another important point is that the receiver stack traces do not have to be correct. A receiver stack trace only has to be comparable to other nearby receiver stack traces. So long as stack traces are unfocused or distorted similarly, they are comparable. The same concept for shot stacks. So long as they are distorted similarly to their neighbors, they are comparable. There are situations where it is better to stack only the traces on one side of the shots and one side of the receivers. This is particularly useful in situations where there are sudden changes in the near surface, such as entering a swamp or crossing a riverbed. An example setup to do that is shown above using the key sign range limit parameters. If the traces have been updated with geometry, see my examples for su-geom-csv from SPS2 files, then the shot station is in key grn LOF and the receiver station is in key gaps. A similar setup can be used to limit the azimuth range of traces that are being stacked. Azimuth can be computed by the SU azimuth program. This may be particularly useful for 3D surveys, again, where there are sudden changes in the near surface. Yes, this is all quite cryptic. You will understand when you get a survey with sudden changes in the near surface. Now, you may wish to update the statics seen in the shot stacks or receiver stacks by hand. This can be done by the su-geom-csv program and other ways, I'm sure. Here is an example setup from Demos Geom3D su-geom-csv. The input CSV file looks like the following, but many variations are allowed. Typically, surveys have more than one shot and one receiver with a time shift. So I have put various time shifts on all shots and receivers of a fake 2D survey. All these time shifts were added surface consistently. You recall this means all traces from a shot get the same time shift and all traces to a receiver get the same time shift. I have retained the large shifts on the original shot and receiver. Display of some of the shots with the various surface consistent time shifts. The shot stack of the survey with the various surface consistent time shifts. The large time shift on the original shot is still visible. The receiver stack of the survey with the various surface consistent time shifts. The large time shift on the original receiver is still visible. The CDP stack of the survey with the various surface consistent time shifts. The SU res stack program is designed to find surface consistent shot and receiver statics. It has many parameters of which I am not familiar. Many relate to amounts of shots and receivers and so on. Their defaults are sufficient for the small fake 2D survey used in this video. SU res stat assumes shot numbers are in the FLDR key and CDP numbers are in the CDP key, and receiver numbers are in the track F key. So I used SU change header word to copy gaps key value into track F. The statics from SU res stat can be applied by SU static. Option headers equals 3. An issue I encountered with SU static is that I had to zero its input trace sstat and gstat keys just in case there were already static values in them. Results follow. the shot stack after su-res-stat, the receiver stack after su-res-stat, the CDP stack after su-res-stat. The results from su-res-stat are not perfect, but are an improvement. I assume su-res-stat options can be set up better than just using defaults like I did. Note, it is my belief that su-res-stat will function for 3D land surveys, but you will have to make sure its shot identifiers, FLDR key, are unique numbers. And you will have to set its receiver identifiers, TRACK-F key, to unique numbers computed from the GRN, ORS, and GAPS keys, which SUGEOM CSV sets from SPS2 files. Obvious question. Since the time shifts can be seen in the shot stack and receiver stack, why not use a picking program or a cross-correlation program to produce the statics from those stacks rather than just viewing them? Answer, good idea, but only up to a point. Determining crude, short spatial period statics using shot stacks and receiver stacks is reasonable, but determining long spatial period statics requires more sophisticated techniques, such as refraction statics, near-surface modeling, or programs using similar principles as su-res-stat. Next, a few uses of su-stackup that are not related to statics. This is a shot stack again, but one of the stack traces looks odd. This may indicate a geometry error at that shot. Naturally, you can also see geometry errors in the receiver stack. Sure enough, there is a geometry error at the shot. There are a few usual ways this occurs. The shot XYs could be wrong, or the shot traces could all have been assigned to the wrong receivers. For instance, an SPS2X file could have the wrong receiver segment values. Now, the slow layer does not just have varying thicknesses. It also has varying velocity within it, and also varying rock properties. Varying velocity will also cause surface-consistent static differences. Varying rock properties will cause amplitude differences. Dealing with that is called surface-consistent amplitude compensation. Varying rock properties will cause phase amplitude wavelet differences. Dealing with that is called surface-consistent deconvolution. As well as surface-consistent statics, the shot stacks and receiver stacks made by su-stackup can also show when there are surface-consistent amplitude differences and surface-consistent wavelet differences. So you can see shot stack traces of different amplitudes. Here, just one shot. Or you might see a change in wavelet, change in near-surface properties. But general discussions of surface consistency is an extensive subject, well beyond the scope of this video. I continue with another example use of su-stackup not related to surface consistency. The su-bin-big CSV program will combine multiple CDPs into bigger CDPs. For instance, the above setup will renumber CDPs 8, 9, 10, 11, 12 to CDP number 10, and then increment by 20, and renumber CDPs 28, 29, 30, 31, 32 to CDP number 30, and continue the same way by increments of 20. Any trace with a CDP number not in any of these ranges is deleted. Note, neither su-bin-big CSV nor su-stackup require that input traces be in any particular order. The CDP stack made by su-bin-big CSV and su-stackup from the simple dipping 2D survey. Now there are a lot less stacked CDPs. No surprise. Now I have modified the previous script. The SU bin big CSV program still just combines multiple CDPs into bigger CDPs. But now program SU change header word is used to compute an offset bin number by multiplying the offset values by 0.05. Since the offset key is integer, this truncates to integer. And SU StackUp now stacks on CDP and offset keys. This results in stacking into offset bin numbers within each big CDP. The second SU change header word resets the offset key back to the offset value at the center of the bin. The next wiggle display shows the result. Stack of NMO corrected traces into big CDPs and offset bins. A final step is now added to the script. The SU NMO program inverts the NMO that existed on the input traces. Remember, the input traces had NMO applied, which is why they could be stacked into their offset bins. The result is CDPs with traces have been stacked into regular offset intervals of 20. Take note that this simple 2D survey does not originally have offset intervals of 20. A wiggle display follows. Inverse NMO correction applied to stack by big CDPs and offset bins. So, why would you want to employ the previous technique? Well, sometimes you have nearby surveys with different offset intervals. It is easier to compare them with the same offset interval. Also, 3D surveys tend to have large variations in CDP fold and offset values. Producing super CDPs containing regular offset intervals helps to see what is going on. I conclude with a few details about points 4 and 5 from the beginning of this video. Point 4. SU StackUp stacks in double precision before outputting normal single precision traces. More accurate and more consistent than SU Stack. Just to be clear, there's nothing wrong with SU Stack, as far as I know, but SU Stack stacks into a float buffer, which is single precision. Float values have about 7 digits of precision. This means, for instance, that SU stack with traces sorted by CDP and increasing offset will produce slightly different output than SU stack with traces sorted by CDP and decreasing offset. But SU StackUp stacks into a double buffer, double precision. Double values have about 16 digits of precision. Therefore, trace order has almost no effect on its output amplitudes. But I did not code SU StackUp to stack in double precision because I thought SU Stack was too inaccurate. I coded SU StackUp to stack double because I knew that it will be used to stack from any input order. And I did not want differences in the output stack just because the input is in different order. That is, I did not want a CDP stack by SU StackUp to be slightly different if your input was shot sorted rather than CDP sorted, and so on. Okay. Point 5. SU StackUp makes each output trace header from the input trace that has the minimum offset distance for that output location. Unlike SU Stack, SU StackUp does not zero the offset key. In fact, SU StackUp goes out of its way to output the entire input header that has the minimum offset distance, except NHS key, which is reset to amount of traces summed. This means that for a CDP stack, the output header has values from a usually quite near shot and receiver. For a shot stack, the output header has values of that shot, of course, but also from a usually quite near receiver. For a receiver stack, the output header has values of that receiver, of course, but also from a usually quite near shot. The SU StackUp documentation of May 2023 follows, just so you can read it here conveniently.